Hello everyone, today we are doing section 5.1, plane curves and parametric equations. We're going to start considering curves which are not graphs of functions. For example, let's consider a circle. Well, some circle, let's consider a circle with radius 1. Why it's not a function? You draw a vertical line over here and you see that it intersects vertical line in two places. So this graph is not a function, but sometimes we still need to deal with curves like this, which are not functions, and use actually some stuff we developed for functions. So what are we going to do, guys? We are going to represent this graph as two functions instead of one, because it does not work for one function. The idea is next. Imagine that you have a little ladybug moving around this circle. And you have a timer over here, stopwatch, and you can kind of record position of ladybug versus time, something like this. You put time over here, x position, y position, and like time equals 1, x equals something, y equals something, time equals 2, well, something, something. Well, if we consider x as a function of t, it's actually going to be a function. It's not going to intersect the vertical line anymore two times. Major reason is that ladybug can be just at one place at one moment of time. Means that, for example, at t equals 1 second, it cannot take two different positions, x1 and x2. It's either at x1 or at x2, which means that x automatically is going to become a function. Same is going to be true for y. Y of t is going to be a function too. Again, same reason, ladybug cannot be at two different places at the same moment of time. Instead of one equation, which was looking like this, x squared plus y squared equals 1, which was the equation of a circle, we are going to have two equations. But these two equations are going to be functions, and they're going to be more convenient for us to use. So, what are going to be these equations? Well, it depends on how ladybug is moving along the circle, right? What we can do, guys, if you look at this equation, you probably see a similarity of this equation with Pythagorean identity. Cosine square of t plus sine square of t equals 1. You see? Very similar, right? Square, square, and equals to 1. So what we can do, we can say that x equals cosine of t and y equals sine of t. And we got just parameterization of this curve. How fast ladybug is moving around the circle? Well, to calculate this, we'll need to find how long it spans along like one round, one circle. So usually, because the motion is going to be like periodic, we are going to calculate the period. Period is 2 pi over omega. In this case, omega is 1. You remember this? So the period is going to be 2 pi seconds. So which is going to be around what? 6 seconds, right? 6 seconds makes one circle. Well, that's how fast it's moving. Can it move faster? Yeah, it can move faster. It can move twice faster, 3 times faster. Then we are going to have a different number over here. For example, how to make it move twice faster? Well, I'm going to put 2 over here and 2 over here. And that's going to give me omega, which is equal to 2. And the time for one circle is going to be pi, which is around 3.14, just 3 seconds. Okay? Let's consider a couple of examples of parametric equations and how we graph parametric equations. Here, everything was already kind of pre-designed, right? We did know that it's a circle, and kind of we assume that the parametric functions are sine and cosine. But let's consider something which is like already in parametric form, and how do we graph parametric equations if somebody creates them for us. So we're going to start with first example. Example 1. We're going to graph parametric curve x equals 3t squared, y equals 2t, and t is not going to be from negative infinity to positive infinity. T is going to be between negative 2 and positive 2. So we kind of don't watch ladybug before negative 2 seconds and don't watch ladybug after 2 seconds. We just watch it for 4 seconds. How can we graph this parametric curve and find out how ladybug is moving? what I'm going to do, I'm going to do the table. In this table, I'm going to have different t's, different x's, and different y's. And then I'm going to use x and y as coordinates of points and kind of graph the graph. So what I'm going to do, guys, I'm going to start with -2 and then do -1, 0, 1, and 2. I think here I'm going to put equal sign. It's going to be like easier for me. Because if I don't include the point, why do I calculate the position at this point? So what I'm going to do, I'm going to take t equals -2, plug it in over here, get 4 multiplied by 3, which is going to be 12. That's x. -2 over here is going to give me -4. -1 here is going to give me 3, -1 here is -2, 0 and 0 are going to give me 0, 0, and 1 is going to give me again 3 here and 2 here, and 2 is going to give me 12 here and 4 here. Well, I do have kind of 5 points which I can use to graph this curve. X, Y. Well, because I do have like large axes here, like 12, I'm going to label 2 units, 4 units, 6 units, 8 units, 10 units, and 12 units over here. And same over here, 2 units and 4 units, -2 and -4. I'm going to skip 1 unit. Okay, let's graph all the points and see what way the bag is going to do on our graph plane. X equals 12, y equals -4, so it's 12, -4, the point somewhere here. So I'm going to label it t equals -2. X equals 3 and y equals -2. 3, somewhere here, -2, the point is here. Next point is 0, 0. Next point is 3, 2, somewhere here, symmetrical to this one. And the last point is 12, 4. 12, 4, somewhere here. I'm going to now connect it in a smooth curve, and you probably can recognize a parabola, right? Which is going to be the piece of the parabola between these 2 points. This is point t equals 2, and how Ladybug was moving along this curve? Moving this way or moving this way? We'll know that usually time moves like from negative direction to positive, so Ladybug was moving in this direction. Parametric curves are usually oriented. Oriented means that it's going to be a different curve if you set it differently, and direction is going to be important over here. Which direction somebody is moving. Okay, now what can I do to graph this without doing a table? Well, because, you know, table just 5 points, maybe I just did not graph them very accurate, and then that's why it's looking like a parabola. So that was way number 1 to graph parametric curve. Way number 2 is going to exclude t from these 2 equations and see what kind of, you know, curve I'm going to have if I express it as only curve of x and y. What I'm going to do, I'm going to solve the second equation for t. I'm going to write down the t equals y over 2 from second equation. And then I'm going to plug this t into my first equation. So write down that x equals y over 2 squared, which is going to give me x equals 3. Square of 2 is 4, and y squared. So that's how my curve is supposed to look. Well, guys, you probably can recognize parabola. Normal parabola looks like y equals x squared, right? Here we have x equals some coefficient y squared. Means that it's not going to be normal vertical parabola, but it's going to be a horizontal one. And yeah, our graph was correct to graph this horizontal parabola. Okay, let's move to my next example. And I'll need to erase all this. Erase it. So in the next example, somebody will give me a graph and they'll ask me to find parametric equations for this graph. Graph is going to be very obvious. What graph of what is this? Example number 2. Okay. Somebody gives me a graph of half circle. Something like this. -2, +2, x here, y here, origin over here. So somebody gives me a graph of half circle with radius 2 and tells me that motion happens from this point towards this point. And they're asking me to find out parametric equations of this graph. What I can do? Well, I know equation of a circle with radius 2 is going to look like this. X squared plus y squared equals 4, right? That's radius 2. Square does not look like square. What I'm going to do, guys, I'm going to divide by 4 these equations. I'm going to write down x squared over 4 plus y squared over 4 equals 1. I'm going to represent 4 as a square of 2, so I'm going to write down x over 2 squared. If I square x and square 2, I'm going to get x squared over 4 plus y over 2 squared equals 1. Now I'm going to compare it to Pythagorean identity. Cosine square of t plus sine square of t equals 1. You see that if we kind of set up x over 2 equals cosine of t, then we are going to have x equals 2 cosine of t, and y over 2 equals sine of t is going to give me y 2 sine of t. This is one way to do parametrization of this curve. Now, because I'm not given the whole circle, I'll need to kind of give restrictions on t, right? From which t to which t I'm going to move. I'm going to start with this point. The beginning point has coordinates. X equals 2, right? So I'm going to plug it into my equation and try to find which t corresponds to this. Well, I see that 2 and 2 here cancels, and the cosine of t equals to 1, which tells me that t equals to 0, right? So my first point is t equals 0. These are equations. And what is going to be my last point, the terminal point? I'm going to do the same. I'm going to plug in minus 2 into my first equation. So I'm going to write down minus 2 equals 2 cosine of t. From where negative 1 equals cosine of t, from where t equals pi, right? So restrictions on t are t is from 0 to pi. T is from 0 to pi. So my ladybug was moving from here to here when t was moving from 0 to pi. Okay, so we found parametric equations, we gave restriction, we can move to our next example. Our next example is how do we convert the function if it's given as equation to parametric form. Let me write this. Okay, example number 3. Y equals x squared minus 4, and somebody is asking me to convert it to parametric form. They don't give me any restrictions on x and y, means that this is parabola, right? Shifted 4 units down, they want to have a whole parabola. So there are many ways to do parametrization of any Cartesian curve. I'm going to show you a couple of different ways just to make sure that you understand that parametrization is not unique. So way number one, what I'm going to do, I'm going to set up x equals t, and then substitute it over here into my equation, t squared minus 4. You see, I got a nice set of two parametric equations, and this is the simplest way to do parametrization. Just set up one coordinate to t, and then calculate what is going to happen to the second coordinate. It's not necessarily supposed to be x equals t, you can do y equals t. Make sure that when you do parametrization, it's going to cover the whole graph. Way number 2. I'm going to set up x equals t cubed. Then what is going to be y? If I plug in t cubed here, it's going to be t to the power of 6 minus 4, right? Square and cube are going to multiply and give me 6, power into the power. So another way to do parametrization. Works also well. Can I do parametrization this way? Way number 3. Can I set up x equals t squared and y equals t to the power of 4 minus 4? Unfortunately, because I want to know how whole graph is going to look, this is not going to work, because for this way, x is always going to be greater or equal than 0. Just because you express x as a square of something, a square is always positive. So this parametrization is going to describe only half of this parabola. Let me grab this parabola so you can understand what we are talking about. So this parametrization is going to work only with one branch. If you just need one branch, it's going to work. If you need the whole parabola, these two are better. Okay. Also, let's imagine that we use a cosine instead of like t squared. Set up x equals cosine of t. What is going to be bad about this parametrization? We know that cosine of t actually is restricted between -1 and 1. So this parametrization is going to describe only axes like, let me see, from somewhere here to somewhere here. It's going to describe only a little piece of the curve. And all other axes are not going to come into that, just because cosine cannot go bigger than 1 means that just only one interval is going to be described by this parametrization. So usually you're pretty free to choose your parametrization, but you're supposed to look at like what part of the curve you want to describe. Okay, I'm going to write down 2 problems and ask you to solve them yourself, or let's say do as much as you can, and then check how I solve it and compare your solution to mine. Okay, first problem, problem A, x equals the square root of y. I'm asking you to convert it to parametric form. And the second problem is x squared over 4 plus y squared over 9 equals to 1, same parametric form. I'm going to count to 3 and give you solutions. And if you kind of stop the video, you can try to solve it yourself and then check my solutions. So 1, 2, 3. I'm going to start solving case A. Well, here I think good idea is to set up y equals as t and x equals as a square root of t. Are we going to have any problems with kind of, extraction of a square root of negative number? Or not if we are going to set up t greater or equal than 0. From this curve it's obvious that y cannot go below 0, cannot be negative. If you use negative y, you're going to extract the square root of negative number. So that's our solution for first problem. For the second problem, whenever you see square plus square equals to 1, you're always supposed to recall Pythagorean identity. So what it looks like, a cosine square plus sine square equals to 1. So you can set up x over 4 equals cosine of t, which is going to give you x equals 4 cosine of t, and y it's over 4, by the way. It's supposed to be over 2. Y is over 2. Well, I want to do cosine square here, right? So actually I'm supposed to kind of write it down as a square of something here and a square of something here. Means that they're going to be x over 2, not x over 4. Also y over 3 equals sine of t, from where y equals 3 sine of t. Do you remember what kind of curve describes this equation? Well, think for a couple of seconds. Actually, it describes an ellipse, right? And numbers underneath, squared numbers, are going to give you the size of this ellipse. In x direction 2 units, in y direction 3 units. Right? Something like this. And that's going to be like possible parametrization. How fast the ladybug is going to move around this ellipse? Well, the period is going to be equal to 2 pi over 1, right? Omega here is 1, so it's going to be like 6 seconds, around 6 seconds. If you change a coefficient here, put over here 2 or 3, it starts going around the ellipse faster. Okay, you can make it also slower. Okay, I think that's all about this parametric curves. Do your homework, ask me questions if you have. Thank you.